So what are we actually studying today? We're going to study a thing called symmetry and transformations. The first topic we're going to study is a thing called the even function. This satisfies specifically fx is equal to f of negative x for all x. X in the values of x which are in the domain. So all the x values in the domain. In this case, this is referring to symmetry about the y-axis. So if you weren't able to get the symmetry concept in the first unit, we're going to make sure that we get it this time. Okay? So, for example, let's say I have a graph that looks like this. This graph is considered symmetric if I mirror it on the other side of the y-axis. Okay? The next concept we have is a thing called the odd function. Now, when you talk about an odd function, here's what you know. That f of negative x is equal to negative f at x. You know what? Let's go back to the previous part that we were doing just now. I'm going to change that. I'm going to change what we have up there to say the following. We're going to change that part where it says f of x equals f of x. I want to have f of negative x is equal to f of x for the satisfying for the even function. So that is important, so highlight it. And then for the odd function, f of negative x is equal to negative f of x for all x in the domain. Now, what this really means, it's symmetric about the origin. So if you think about it, we substituted negative x for x, and then we also flipped the y. So, and then finally, you flip it. So it's like you mirror the x, that's what the f of negative x is, and then we flip the y values from negative to positive and positive to negative. So an example of this would be a graph that looks like this. So the graph would look something like a cubic function, which you'll learn about later on in this course. Okay, so now let's go and use the material that we're using, that we have here, to do this next problem. So let's put a little box in the top corner of our screen. And every time we do these problems from now on, we'll make sure that we have that in the top of our sheet. So if I'm looking for something that is even, that means f of negative x is equal to f at x. If I'm looking for something that is odd, we're looking for f of negative x is equal to negative f at x. So now let's determine whether these functions that we have here are even, odd, or neither. So remember, even means f of negative x is equal to f of x, and odd means f of negative x is equal to negative f at x. So here is our first problem. So f of x is equal to x to the negative 5. Here's the solution. The key idea is to start by saying f of negative x and substituting directly into our original equation. So you notice that I put a bracket around my substitution, right? So now when you go and expand that, you can apply the -1 that's actually sitting in front of the x, and you raise that to the fifth, and you have x to the fifth. -1 to the fifth is always negative since it is an odd power of -1. So the answer is -x to the fifth. And we know that from our original equation that f of x is equal to x to the fifth. So this is really negative f at x. So therefore, f at -x is equal to that. So therefore, this is an odd function. Because when we look at our description, if I substitute -x, I get negative f of x, which is what we expected. Okay. And now that is our solution. So let's try another one. So now that we have h of x is equal to x minus x squared, let's go and solve it. So every time we solve, we start by substituting h of -x in this case. So we have h of -x, and we substitute all our x's with -x. So we go negative x minus -x squared. So x squared and x squared is going to end up being just x squared. But the minus sign in front stays there. And then the minus x becomes minus x squared. So in order to kind of make this look like our odd function, I'm going to try and pull out a minus sign from both of them. So you end up with minus x plus x squared, which doesn't look like h at x at all. And there is, in fact, no way to manipulate this. So therefore, once we cannot change it to either fx or negative fx, we automatically say that this is, therefore, this is neither. Is neither. I think I spelled neither wrong. It's neither odd nor even. Take a moment and copy that down. The next thing we're going to look at is transformations of vertical and horizontal. A long time ago, you studied a thing called transformations, right? And to transform means to move something to the left or right, up or down, diagonally, whatever. But we are going to focus on the vertical and horizontal translations of this function. So if I have the equation y is equal to fx, where the value c is greater than 0, this will allow us to find out what's actually happening with our curve. So we would say for y is equal to the original function, If we add c to that, then we shift the graph up exactly 3 units. For y is equal to fx minus c, so we're taking away from it, this is a vertical translation or a shift down 3 units. So when we have a function where we change x to x plus c inside of it, this is going to be a horizontal shift left c units. Please make sure that you change these values of 3 here to be c units. Okay. Now, for part 4. For y is equal to f of x minus c, so you're replacing x with minus c, we've basically moved all of our graphs to the right, all of the points in the graph to the right, exactly c units. So now what we need to do is we need to talk about vertical stretches and shrinks. Copy that down and then get ready for the next thing. Now, you learned about vertical stretches and shrinks a long time ago, okay? Here's what we will start with. So we start with y is equal to f of x. If y is actually applied to f of x, so what it's done is it's actually, if our a value is bigger than 1, we say that our graph is stretched by a factor of a, and that's only if our a value here is greater than 1. And so now, if we have a graph that looks like this, y is equal to a f at x, where our value of a is less than 1 but greater than 1, then it's a vertical stretch. And we say that is, we should say that this is a vertical stretch. Sorry. It's vertically stretched by a factor of a for the first one and vertically compressed. So if you have a number that's between 0 and 1, this is compressed by a factor of still a. So if a was 0.5, you would say it's compressed by a factor of a. The last thing that we have to look at is a thing called vertical reflections. So if we start with a vertical reflection that has y is equal to fx, then if I have y is equal to negative fx, this is a vertical reflection in the x-axis. So I want you to imagine the x-axis is here, and this was my original graph, y equals fx, and then if I apply negative fx, it just flips the graph. That's all it is. Okay, so it flips it to the other side of the x-axis. So just take a moment and copy that down, and then pause the video if you have to, and move into the next page. So here's our first example of something where I want you to tell me what's happened to the original graph. So imagine I give you this arbitrary graph that I want you to look at, okay? I'm going to call it y is equal to fx. It could be y is equal to x squared. It could be y is equal to something. It doesn't matter, but I'm giving you a general function. Now, I'm going to ask you to describe the transformations and then sketch the basic graph of what it looks like. So let me show you what the original graph of f of x looks like. So imagine our graph looks something like this. There. So our graph kind of looks like that, okay? So once our graph looks like that, and I give you this possible graph, y is equal to f of x plus 1. Now, if you're looking at this, I need to know what the solution is. So remember, the original graph, all of our y values are just being added 1. So all this is a vertical shift up 1. And what I'll do is I'll graph that in green. So remember I said I was going to graph this in green. So all of the points, all of the key points of my graph are actually shifted up 1 spot. And then I connect the dots like I was in grade school again. Connect the dots, tra-la-la. So our graph has shifted up. So it's actually moved up 1 space, also known as a unit. So now we said it was a vertical stretch up. So imagine if I had another problem where I had y is equal to f of x, f of x plus pi. Now, the rule is if you have x plus pi inside a bracket, what that means is that this thing has moved left pi units. Now, if I'm looking at my graph here, if this is pi, and this part here is negative pi, then all we've done is we've taken all of these points and moved them exactly 1, 2, 3 spots to the left. So this point here gets moved 3 spots, 1, 2, 3. So that's where it's supposed to be. And there's my first point. And then I move the next point that's my base graph to the left 3 spots. And then I do the same for the next spot. 1, 2, 3. And then this one where I have my red spot here, right here on the x-axis, shift it over exactly 3 spots. 1, 2, 3. And the last point here moves 3 spots to the left. 1, 2, 3. And then we connect our dots and make a nice curve. And all we did was moved it left pi units. That's all we did. And our last problem of the day. So imagine we start with the graph y is equal to x squared, okay? So what we got to do is we actually have to take the time and graph it. So every tick on your graph, make it 2, 2, 4, 6, 2, 4, 6, -2, -4, -6, -2, -4, and -6. So what we're going to do now is we're going to graph y equals x squared. So y equals x squared starts at 0, 0, but then the steps for x squared are 1, 3, 5. Over 1, up 1. Over 1, up 3. Over 1, up 5. 1, 2, 3, 4, 5. We have our half parabola. Reflect it along the axis of symmetry, and we get a graph that looks like this. Now, the next thing that we have to do is we have to look at our equation here. And we start when we read our basic equation that we're going to go and show all the transformations. Our graphs are going to change accordingly. So x squared turns into, so y is equal to x squared turns into y is equal to -4x. No, it turns into negative, so all the points get flipped. So let's do that first. So we take our graph and we write -x squared. So all our steps are -1, -3, and -5. And I'm going to use red to describe that. So here are our points. Oops. And then we graph. So since we're moving from right to left, the next number that's in our graph is a 4. So that 4 tells us that y negative x squared turns into y is equal to -4x squared, right? So -4x squared means that all our values that were for our steps are now -4, -12, -12, and -20. So instead of being 1, 3, 5, all we've done is multiplied all of those by 4. So now I can really only get a couple of points on my graph. So I'm going to make that green. And as I do this, you should do the same on your own graph. So you kind of show that it's being stretched. So it starts at 0, 0 before, and then now we move all our points. We go over 1, down 4, over 1, down 12, so it's way off the graph. So I'm actually just going to draw 3 points. And so there is our new graph for y is equal to x to the -x squared. So now the next transformation in our chart shows that we have y is equal to -4 and x minus 5 squared. So now what that allows us to do is it tells us that it moves, that our graph moves left. Nope, not left, it moves right 5 units. So all of the base points for the green graph have to move to the right 5 units. So what we'll do is we'll use a purple for that. So go to our green and we count 5 units to the right. So from the vertex, we count 5 units to the right. So here's our first point. And then we're down 4. We go to our next point, count 4 across, 5 across, 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5, perfect. And then we do for the other side as well. 1, 2, 3, 4, and 5. There's our 5th point. Boom. And now here is our purple graph. The last stage of this would be to take our graph and look at the +6. The +6 tells us whether it moves up or down. If it's +6, it moves our graph up 6 points. So our new graph is this. Y is equal to -4 x minus 5 squared plus 6. So this means we move all the points up 6 points. And we're going to use a different color graph for us. So let's go and use the yellow. So we'll use yellow here. So our points in our last graph, which was the purple graph, have to move up 6 points. 1, 2, 3, 4. From the vertex, we're going to go up exactly 6 units. So our first point is here, nice and big. Our next point is 4 below, so now 6 up is there, and then the next point is there, and there is our final graph. When you do these problems that I give you, I want to see all of the transformations of the graphs. Now, if you don't have graph paper, that's fine. We can take the time and make some graph paper for you. Have a good day. So for the homework for this section, you're going to do page 64, which I'll provide for you. You're going to do questions 1, 5, 9, 13, 17, 21, 23, 27, 33, ABCD. Now, here's the deal. Understand this material because it is important, okay? We need this for our graphing at a later date. Take care.